Okay, so we're going to look at using Riemann sums and expanding that along with some summation notation and infinite limits to find exact area under a curve. Riemann sums generally is used for approximations, but it can be tweaked quite a bit to find an exact area. For in this video, I'm going to be using a handout that I gave to my students. If you want to print that and follow along, you can go to bit.ly/exact area. That is case sensitive, so make sure you do a capital E and a capital A, and you can find the sheet that has the problems that I'm about to look at. So let's talk about Riemann sums, and in this example we're going to be using a right-handed Riemann sum. That really doesn't make a huge difference. It works either way if you want to use left points or mid points or something like that. So what we have here is some generic function that starts at some value x equals a, it ends at some unknown x equals b, and I want to start by setting up just the general formula for a right-handed Riemann sum. And in this problem, my delta x is consistent. I kind of free-handed all of these rectangles, so if you were to actually measure them, you'll see some inconsistencies. But we're going to pretend that that delta x is always the same, and so the area of each of these rectangles would be the base times the height, so the delta x times f of x sub 1, delta x times f of x sub 2. And so right-handed Riemann sums would be exactly that, delta x, f of my first x coordinate, plus delta x, f of my second x coordinate, and so on and so forth. All right, so there's the rest of it. I just kind of skipped from x sub 3 to x sub n minus 1. And in this, I'm going to do a little bit of algebra. I'm going to do a little bit of algebra here. The base of all these rectangles is the same, so I could factor out that delta x, giving me delta x times f of x sub 1 plus f of x sub 2, and so on and so forth. There we go. So I factor that out, and there's what I'm left with. I could, and just because it's going to come in handy a little bit later, I'm going to move that delta x. Instead of saying delta x at the front, I could actually take this delta x and move it all the way to the other side. And so I'm going to move my delta x to the right side, so for something you'll see. All right, so now what I'm going to do is take that formula, and we're going to convert it to sigma notation. If you notice, we are adding a whole bunch of stuff here, and when you have a repetitive pattern of addition, you could write that formula right here in sigma notation or summation notation. And so what we are adding up is a whole bunch of f of x's, but the subscript of x is changing. And so I'm going to do f of x sub I, and we are adding up all of those as that subscript starts at 1 and goes all the way up to n. And then that delta x, I'm going to stick over here on the end of it right there. So it's f of x sub I times delta x, and the sum of that as we go from 1 to n. And that's going to be the base setup for how we're going to tweak this to get exact area. So what we have, if there's a finite number of rectangles, this will be some type of an approximation. But if I want to increase the accuracy, like right now I believe if you counted these rectangles, there's actually 9 that I drew. If I wanted to increase the accuracy, I would increase the number of rectangles. So the more rectangles you have, the more accurate the answer will be. So assuming we're stuck with right endpoints, to ensure a more accurate answer, we would need to use more rectangles or more subdivisions if you want to be kind of technical with it. But we're going to use more rectangles or subdivisions. And if we are sticking with right endpoints, what would I need to do to get the exact area? Well, to get the exact area, I need to take so many rectangles that there is no error in the approximation, which means the number of rectangles needs to approach infinity. So the number of rectangles needs to increase towards infinity. Right, so that's how we're going to get exact area. So we're going to take that formula I just gave you, and so the approximation was the sum as I goes from 1 to n, and we're going to add up the area of all those rectangles, so f of x sub I delta x. And we're going to look at that approximation. And if I look at that approximation and I let the number of rectangles approach infinity, this will give you the exact area. That will give you the exact area once we tweak that a little bit. Okay, so there's our basic setup. There are some formulas you're going to need to know in order for this to work, and some adjustments we'll make to this formula, and that's coming in here. So a few useful formulas to get exact area. First, delta x is b minus a over n to find the base of each rectangle. Going back to the original shape here, your ending point minus your initial point divided by the number of subdivisions does give you the base of each rectangle. And then x sub I, to get that value right there, that specific x coordinate, if we go back, whoops, that's the wrong way. There we go. So if I want to know like what x sub 1 is, x sub 1, if I started at my initial value of a and I moved to the right 1 delta x, so a plus 1 delta x would give me x sub 1. If I wanted x sub 2, I would start at my initial value and I would move to the right 2 delta x's. And so hopefully by now you see the pattern. It's not that hard to see. So x sub 3 would a plus 3 delta x. So if I want to skip that to just some generic x coordinate, my ith x coordinate, it would be my initial value plus my delta x times I. And so that's what we're going to use for x sub I. So it's your initial value plus your change in x times I. And then these next four are just ones that are going to come into play later when we do an actual problem. If you are adding from 1 to n and you just have a constant, like the sum from 1 to n of 3, then that answer would be 3n or c times n. If you're adding your integers, like this would be 1 plus, and I plug in 2 for I, plus 3, plus 4, and so on and so forth. The sum of the first n integers is n times n plus 1 over 2. Here we're adding the first squares, the sum of the first so many squares. So that'll be like 1 squared plus 2 squared plus 3 squared. That's not a 3. 9. There. So on and so forth. That formula is, this is the ugliest of the ones I'm going to put in here. N plus 1, 2n plus 1 over 6. And then the sum of the first n cubes is n squared, n plus 1 squared over 4, which that one coincidentally ends up being the sum of the first n integers squared. So if you square the sum of I, you get the sum of I cubed. Okay, so a real problem where we could use this, and I'm going to do one example and then I'll have another video later doing some other examples. So I want to use Riemann sums to find the exact area under this function on the interval 0 to 2. So my formula, I'm going to start off with the limit as n goes to infinity of the sum I goes from 1 to n, f of x sub I times delta x. Except we know that delta x, I'm going to come over here, delta x is b minus a over n. Well, a is 0, b is 2, so that's going to be 2 minus 0 over n, or just 2 over n. Right? And we know that x sub I is a plus your delta x times I. And we know that a is 0, and we just found out delta x is 2 over n times I, which cleans up to just 2I over n. Okay, so I'm going to take these two things here. I'm going to substitute 2 over n in for the delta x, and I'm going to substitute the 2I over n in for x sub I. So now working out this limit, that's going to be the sum I goes from 1 to n of f of 2I over n times 2 over n. And now we're about to do a whole bunch of algebra. F of 2I over n, we're going to plug 2I n over n in for that x. 1 to n, that will be 2I over n plus 3. Plug it in for x here, times 2 over n. We'll distribute the 2 over n. 1 to n of, that will be 4I over n squared. 3 3 times 2 over n would be 6 over n. And then I'm going to break that into 2 sigmas. So I'm going to make that I goes from 1 to n of 4I over n squared, plus the sum I goes from 1 to n of 6 over n. And in both of these summation notations, I is the variable. I is what we're plugging values in. I'm not plugging anything in for the n squared or for the n. And for that reason, 4 over n squared is a constant. And 6 over n is also a constant as far as the summation notation is concerned. And you can pull constants out of summation notation. So I'm going to write it like this and make it 4 over n squared times the sum as I goes from 1 to n of I, plus, and then I'll have 6 over n times the sum as I goes from 1 to n of, and since there's nothing left inside, I'll just put a 1 there to hold the place. And what I've created here, I have the sum of the first n integers and the sum of a constant n times, which goes back to these formulas that I gave you a minute ago. We're going to use number 4 and we're going to use number 3 right here to get rid of the sigmas, to get rid of summation notation, and this is going to turn into a new limit up here. So I substitute those formulas in for the sigma notations, and then we're about 2 steps away from being done. I'm going to clean this up ever so slightly. That's going to be 4n times n plus 1 over 2n squared. And 6 over n times n is just 6. And now finally I've gotten myself to an infinite limit where I can look at the degree on top and bottom. For this first one, top degree is 2. If I were to distribute the 4n, that'd be 4n squared. So top degree equals bottom degree, so we would divide the coefficients. So the answer to that first limit is 2. 4 divided by 2, plus then I have the constant 6, which gives me an answer of 8, and that is the exact area under the curve, or the line technically, of x plus 3 on the interval 0 to 2. Whew, there we go.